Okay. So last time we talked about this list of items here. I didn't cover everything, but most of it. And then there's some exercises. These are due this Friday. And we talked about, did we talk about random numbers? We did that, right? Yeah. And there's this final exercise here, unit conversion. This is a little tricky, so I'm going to talk about this one now, okay? Are there any questions? You can always interrupt me and point me.
Yeah, with a random generator,
Yeah.
you're talking about, is there a restriction amount of values you want? So let's say if you want to generate like 2 dice, dice can only go from like 1 to 6.
Yeah, these random numbers, 100 random integers, so I don't give a range, but I could have given a range. And I think later on, we will come back to this random number problem later. And later, what I will ask you to do is generate random numbers in a range, in a given range. I'm just going to show you quickly how to do that. And we'll review that later if needed. Let's see, I think it's this one here. We didn't actually we talked about the difference. I didn't talk in detail about this for loop, did I? I think I need to cover that. This is called a while loop, and this is called a for loop. So what both these loops do is repeat a block of statements. The block starts with this opening brace and ends with a closing brace. Those are called braces, or curly braces, or curly brackets. So there are 3 statements. Each statement ends with a semicolon. Statement 1, 2, and 3. In the for loop, there are 2 statements here in this code. You could have 1 statement. You could have 0 statements. You could have any number of statements. And these 2 loops are equivalent in that they produce the same result. They both print 3 random numbers. And you can start, if this is new to you, you can start by looking at the while loop and trying to understand how that works. That typically, not always, but typically a loop has a counter. Here we're using a variable I. We initialize it to 0. Each time we run the block of statements, we increment I. See, there it is. We increment I at each execution of the enclosed statements. And when I gets to 3, then the loop condition, which I have highlighted right here, the loop condition becomes false. When the loop condition becomes false, the loop statement itself is considered complete and done. So the loop is basically, the loop has a loop condition. In the for loop, the loop condition is there. You see it's the same as this one. Except we're using K here instead of I. The loop condition, when we come to the while loop, when execution, actually execution is linear. The first thing we do in this program is we run that statement. We execute it. And then we execute the second statement, which is that one. Then we execute the third statement, which is that one. After we execute the third statement, we execute the fourth statement, which is that one. These are whole statements I'm highlighting. The while loop itself is a complete statement. Now, this is a very simple statement compared to this complex statement. The complex statement has substatements. This while loop has 3 substatements. So you can think of these as child statements. And they're children of this parent statement here. So it has to do, it's like zooming, you look far away and you've got to zoom out, with the binoculars. And when you look close by, you've got to zoom in. So there's different ways of looking at the code. Sometimes you're looking at detail, sometimes you're zooming out, and you're looking at a larger block of logic and understanding it at a different point of view. So this program has 4 top-level statements. And 2 of the statements are loops that contain substatements. The first loop contains 3 substatements. The second loop contains 2 substatements. Now the loop, the while loop, has a loop condition inside these parentheses. I is less than 3. That's a condition. A condition is something that's either true or false. Let me give you an example. Here's a condition. It's raining outside. It's like a statement, right? It's an assertion. That's false, okay? But it's a meaningful assertion. This condition here is a meaningful assertion. I is less than 3. It may be true or it may be false. Now, when it's true, we're going to run the substatements. And then we evaluate the condition again. If the condition still evaluates to true, we run the substatements again, and so on. So when the condition becomes false, at that moment, we no longer execute substatements, and the loop itself, the entire loop statement itself, is now considered to be finished or done. And we move on to the next statement in the code. That's how you think about it. That's how you think about loops. So these lines will run exactly 3 times. We're going to print 3 numbers. If we start at 0, we let I be 0, this statement here will be true 3 times. And in the 3rd time that it's true, and we increment I becomes 3. When I becomes 3, the loop condition is now false. And when the loop condition is false, we do not execute the substatements, and we're done. So this is how you're going to see it in this class, because this is how we see it normally in code. You look in your textbook or any textbook, you'll see the loop constructed like this. One sec. But you're probably used to thinking like that. Start at 1, and while I is less than or equal to 3, let's do everything. So this loop will also run exactly 3 times. But that's not what you see in practice. You normally see that. As I explained last time, this form of counting emerges out of the hardware level. You have a question?
Yeah, are we going to ever do the do while loop?
I'm not going to cover that, but you should learn it.
Okay.
Yeah. Do while loop, you can learn that on your own. It's not as, these are the 2 most commonly used loops. Do while is another type of loop. And, if you're going to be a programmer or a computer science major, you should look at that. But you won't see that used as frequently as these 2 loops. All right. So now the while loop is pretty straightforward. It's got the loop condition here, and then it has the body in there. The for loop is a little different. It's more compact. It has 3 sections. This is the first section, which is an initialization. This initialization is equivalent to this line right there in the while loop. In the while loop, we declare a variable which is functions as a counter, and we initialize it. In the for loop, in the first section, we declare a variable to be used as a counter, and we initialize it. Just like the while loop situation, this initialization code runs only once. It is not repeated. This first section in this for loop syntax, this code here that I have highlighted only runs once. It is not repeated. And it runs before everything else. And then the third section, look, the sections are separated by semicolons. The second section is the loop condition, and that's checked before executing the block of statements that are substatements. If the loop condition is false, the for loop is finished. We don't do anything else. We just go on to the next line. There is no next line, so we're finished with the program. We terminate. And the third section here is an end of loop operation. After you execute the body of substatements, the body of the loop, after you execute those statements, you'll execute this end of loop operation. So I put plus plus I down here. This is at the end of the loop, right? So here in the for loop, you put it right there. You can see this is, got more lines of code. This is more compact. And you'll see there's different situations. In some situations, you want to use a while loop because the loop condition is complicated and it's not based on simply incrementing a counter. But if you're controlling the execution of your loop by incrementing a counter, then most programmers will use a for loop for that. You can still use the while loop to get it done, but it just won't. It's not the commonly chosen solution. All right, so I'm going to go with the for loop. That's it for loops. And loops are, I can't imagine, I think that may be the most important thing, that a loop and a conditional if statement. Those two things are probably the most important things that you can master in this class. Just the if statement and a loop. So conditional and looping. But you have to have those to write a meaningful program. You don't have to have functions, but functions help organize code so that it makes things readable. So a lot of what we're going to study is syntax and techniques that improve human readability, but they're not necessary to implement an algorithm with. But most algorithms require loops and conditionals. So those are like core needs. So in this for loop, and I'm going to put this all in one line here. So we do left to right evaluation. The first thing we do is we output a random number. Well, we call the rand function. It returns a random integer. And then this code here, this expression I've highlighted, evaluates the cout that becomes the left-hand side of the second output operator, so that we output a new line character. Let's see what happens when we run this. Three random numbers, which change each time. And they're changing each time because we're seeding the random number generator with the number of seconds that have elapsed since some epoch. Now, let's suppose we wanted our random numbers to be between 1 and 10, or 0 and 10, because that's easier. Then what we can do is divide the integer that rand returns. We divide by 10. And we just take the remainder. We ignore the result. So if we get 21, if rand returns 21, let's suppose that rand returns 21. Then we do 21 divided by 10. 21 divided by 10 is 2 plus 1 over 10, right? It's 21 over 10. But what this is called a modulo operator. So this would be 21 mod 10. So the modulo operator just is interested in the remainder. So we toss out the result, or the quotient, I guess, and just look at the remainder. So the remainder of 22 mod 10 is 1. I'm sorry, 21 mod 10 is 1. So you know what the modulo operator is, everybody? Math majors in here, non-math majors should also know, yeah.
So is that something that we could use for the conversion?
If you need to use it, you can, yeah.
So, remainder?
I'll do the conversion next. Yeah. I don't think you need it.
Yeah, I was just thinking maybe like mod 12 or something.
You can try it. You might. There's a solution that uses the modulo operator, but I'll present a solution that doesn't use it. So rand mod 10, what are the values that are going to be produced here? Well, 0.
0 to 9.
Huh?
0 to 9.
0 to 9, exactly, 0 to 9. So there's a 9, there's a 1, there's a 0, okay? We're not going to get -1, we're not going to get 10. We won't get 10 because 10 mod 10 is 0. Right? We go around the circle already. But suppose I wanted the digits 1 to 10. How do we get 1 to 10? +1 is pretty simple, right? Put the +1 there. So you can play with this and get the range that you want. See, there's a 10, there's a 2. You're not going to see a 0 because you always add 1. So when it produces 0, you're just going to get a 1. All right. I'm going to use the copy command here to create file ex4.cpp. There it is. And let's do the other problem. I don't think we need that, so I'm going to take that out. See, that's clean. You shouldn't leave header files in there that the code doesn't rely on. You shouldn't leave declared variables in your code that you don't use. You should keep the code clean. If you don't keep the code clean, it's hard to read it. It's hard to maintain it. It's hard to debug it. It's hard to extend it. And you're always debugging, you're always extending. That's the nature of programming. So you've got to keep it clean. It's like your bedroom at home. You got to keep it clean. Okay? You can think more clearly when you have a clean room. And you got to keep your code clean. And by the way, when you submit these lab assignments, we grade them on cleanliness. And Sushmita was pretty soft on you guys last time because some of you pasted in code and the indentation wasn't good, and I think she took a point off. So you got to pay attention to that. Look at my code. Do you see how I indent the code? This function here, this is the opening brace right there. And this is the closing brace. And everything in between the opening and closing braces is indented to show inclusion, to show that what's included are substatements within a larger construct. And the same thing with the for. This is a single statement right there. That's one statement with substatements. The substatements are indented. And I'm using tab here. You don't have to use a tab. You can use spaces if you like. Don't mix tabs and spaces. If you're going to use tabs, just use tabs. If you're going to use spaces, just use spaces for indentation. As different editors will render tabs with different numbers of spaces. That's the reason for that rule. So, there's two indents here because this line here is inside of the for statement. So you're going to use an indentation to show that inclusion. Show that it's within the for statement. It's a substatement within this parent for statement. And the for statement here is inside of the main function. So we indent that to show that inclusion. It makes it easy to read. This is the most important formatting rule that you should follow when you're coding, is proper indentation. There's other rules too. Like I'm consistent in my spacing. I didn't do, if I was sloppy, I would do like this. See? I wouldn't pay attention to spaces. Maybe I'd do that. Maybe I have a couple of, sometimes the students, they'll submit code that looks like that. And that's terrible. That is not neat. It's too hard to read. So clean it up. If you don't like spaces, that's okay, but take them out of everywhere. Don't just do it randomly. If you don't like spaces and you want to keep your operands close to the operator, you can do that, but be consistent about it in that file that you're working in. Yeah.
What about with comments?
Comments are okay. I mean, use comments when they're needed. You don't over comment the code. You see people like, I'll show you a silly comment, okay? Initialize I to 0. I mean, I got to read this, initialize I to 0, and then I read that line. Oh, that line, you can read that. And that's initializing I to 0. Now, when you're starting out, like many of you are, that comment is okay. Okay? Because it's meaningful to you. But once you have a few weeks done here, you're going to see this line and you're going to know immediately, I'm initializing I to 0. So why do I make myself and others read this comment when I just have to read the same thing in the very next line? So once again, this makes sense if you're just trying to understand the code for the first time and you want to write it out. But later, when it's obvious what we're doing here, you don't need that comment. You see that? So comments are a matter of judgment. Don't over-comment. Don't under-comment. You got to just get it right. Comment for your audience, for yourself, for other people who will be reading the code. But there are no required comments. So in the class, because it's a subjective thing, I'm not going to evaluate comments, in terms of scoring points. I may make comments about it, but I won't score on it. But if you're inconsistent in your spacing, like if you do something like that, that doesn't make sense. Well, unless it does make sense. I mean, maybe you want to line things up in a certain way, but it should be obvious by looking at your code. I like spaces, so I do it like this. But if you don't like spaces and you want to keep them compressed, it's all right. But be consistent. Be consistent in your style. Some people put their braces like this. This, by the way I have the braces in this code, this is the most common formatting technique. Less common would be to do this. I think the book might show it like this. This is less common, but it's acceptable. But whatever you do, if you want to use this form of the brace, then do it everywhere to keep it consistent. Don't mix styles. Stick to one style. If I'm going to use this style, I used to use this style a lot. Sometimes I do. It just depends on the project, who you're working with. If I'm working with other people that are following the style, I don't want the code to have multiple styles. I stick to whatever style is in use. Programming is typically a group activity. Sometimes it's you're alone, and you write code that only you look at, but that's rare. Normally, you're part of a team, and the code is enormous, and you got to keep some rules to keep things readable. All right, so let's look at the next one. Now, I'm not even going to look at the problem. And I want to remind you that I'm suggesting that you use incremental development. So I created a file, ex4.cpp, this one here. I created that file as a starting point to solve problem 4. And I'm ignoring what problem 4 is about. Well, I know that it's a simple program. So I'm just going to print hello, and I'm going to practice, make sure that I don't have any bugs in there. It compiles. It runs. That's my first step. All right, now I don't have to worry about that. Syntax errors from the starting point. So unit conversion, write a console program that converts meters into feet and inches. The program starts by asking the user for a measurement in meters. The program should accept a floating point number. After getting the number, the program computes the number of feet and inches equal to the specified number of meters. The program outputs feet and inches as whole numbers. The program should round the number of inches correctly. Test that your program produces the following outputs for the given input. So if you enter in 1 meter, the program should print 3 feet 3 inches. If you type in 2 meters, the program should print 6 feet 7 inches, and so on. And then here's a constant. That's how many inches are in a meter. And then I have a hint down here. Let's do this problem, but instead of feet and meters, feet, inches, and meters, let's do something else, like liters and gallons and cups. Can anyone think of a good problem other than that? You want to work with liters, gallons, and cups? What do you think? Any? Huh?
Ounces and gallons.
Ounces and gallons? Okay, we'll do ounces and gallons. So we'll go liters to ounces and gallons. All right. So we're going to enter in the liters. So we're going to prompt the user for liters, and then we're going to read it in. Now, liters will be in a floating point value. And then we read it in. And then we're going to print, X gallons and Y ounces. I guess that's how you would do it. It'll look something like that. So look, it's a partial solution. Let's see if it compiles. Let's run it. Number of liters, 3 liters. X gallons and Y ounces. You see, this is incremental development. This is my second prototype. The first prototype, I printed high, or okay. The second prototype, I'm reading in a value that the user enters in. And I'm printing something that looks like I'm getting toward the result. You see this? Incremental development. I'll converge to a solution through the production of a sequence of prototypes that we can run and look at. All right. So the hint is to convert liters to ounces. total ounces is liters times something. How many ounces in a liter? It's amazing that you can do this. Totally amazing. All right, there we go. We just did that in 10 seconds, you know. If this was, when I was your age, you know, I'd have, I go to my office and look this up. Did anybody bring a dictionary? 15 minutes later, we got the number. All right. So I think that's it. It gives us total ounces as a integer. See, we're truncating. So we remember this here is a floating point number. That's a double. And then we multiply by a floating point number. So the result is a floating point number. Let's suppose that this answer here, this answer could be, you know, 1.9. It could be 1.999. Now, how many ounces is 1.999? You say 2, right? So we have to round it. Now the computer will truncate here. So 1.999 will be truncated to 1. So this by itself is going to give us something that is losing information that we don't want to lose. So we just add 0.5 and then we truncate. So 1.999 adding 5, we're going to get, you know, 2.499, right? I think I did that right. And that gets truncated. So we're just going to stop at 2. So that's the easiest way to do the problem. Take the double value that you want to convert and put it into an integer form for the lowest unit, like ounces. We wouldn't do this for gallons, but you do it into ounces. Those are total ounces. So how many gallons do we get? Well, it's the total ounces .64, right? 64 ounces in a gallon.
No, it's 128.
Oh, it's 128?
Yeah. 4 liters or 4 quarts a gallon, so 32 ounces per liter.
Liter? There's no liters, right? It's quarts.
Quarts and gallons, well, we're using liters, that's why it's 33.
Huh? No. I just want to know if you have a total number, how many ounces, how many fluid ounces are in a gallon? Forget about liters.
128. I'm just saying it's 4 quarts, and each quart there's 32
Yeah,
ounces.
that. You don't have to say liter, just quart. Right.
Yeah.
Yeah, okay.
And
So 128, thank you, that's it. 128. I can't remember these things. All right, so it's 128. And now see total, you have to pay attention. What is that operation?
Division.
Well, that's not good enough.
In
Just say division, that's not good enough.
Integer division.
Integer division. That's good. So we lose the fractional part. And that's what we want. If we have 130 total ounces, that's 1 gallon. We don't need 1.002 gallons. I mean, it's not that small, but you know, we don't need, we're tossing out the fractional part because it's the fractional part that will be used to compute the number of ounces. So let's take a look at this. Partial solution. All right, we're doing incremental development. I know this is hard to read, isn't it? Can people see this? I don't know if I can make that larger. That's better, right? All right, so what the heck? Number of liters, 5. That's going to give us 1 gallon, I think.
A little bit over.
Huh?
Over, but yeah.
Well, yeah, all right, but we're only doing gallons right now, so we got 1 gallon there. So now we got to figure out how many ounces. So it's roughly 4 liters to a gallon. You know, more than 4, less than 4, whatever it is. All right, what's the best way to do this? Now it's too big. All right, so we've got the gallons working. Now what about the ounces? So we have total ounces. We don't want to print the total ounces. If we did, what would we get? Nope. What the heck? What did I do wrong? Oh, this int.
1 gallon, 145 ounces.
I'm going to keep doing this. I'll get good at this. Liters, 5. 1 gallon. So it's 169 ounces. So we want to take out 128, right? So that'll be, 41 ounces. So it should say 1 gallon, 41 ounces. So we have to take out, if we had 5 gallons, it was 5 gallons and 169 ounces. If it was 5 gallons, we want to subtract 5 times 128, right? So we're going to subtract the number of gallons times 128 ounces, and that'll give us the remainder ounces that we need. So I am getting used to this. See how that works. So we have total ounces, but that's not what we want. We want kind of like the remainder ounces. So we take the total ounces and subtract 100 and subtract the number of gallons times 128. That should give it to us. And I got to get that show gutter. What did I do?
Let's open up a new terminal.
How do I bring that back in?
Go up to view, maybe. View terminal.
Console. Look at that. Thank you. So we're going to, don't forget to compile. Now we're going to run it. 5 liters. Oh,
Did you save?
what happened? I didn't save. Thank you. It looks like, I think I did save. Oh, I didn't change this. Look at that. Liters, 5. 1 gallon, 41 ounces. Touchdown. Yep, you got it. All right. So that's what you got to do basically to solve this problem. And just run these tests, see if you get it right. Any questions? And you know what? This is the last time I use Cloud9. I mean, for me. But I want all of you to use Cloud9 because it makes it so easy for us to evaluate your work. Now, if you have a question, like I'm stuck on something, and I just said, send me the link. And then I can look at your code directly. And it's very easy for us to help you if you use Cloud9. But it's hard to, you see I'm fiddling with it. I'm just showing you how to use Cloud9. This is the last time I use it. I'm going to use my local console instead, which I have more control over. I can work more quickly. Yeah, I'm recording. All right, so that's that one. Now, what I want to do is talk about the next topic, which we've already been talking about essentially, is algorithms. How to, a computer program is an algorithm. It's a sequence of instructions that solve some kind of a computing problem. And also I want to point out that this topic here, let me look at exam 1. Exam 1 covers command line, expressions, and algorithms. So what I'm going to start talking about now is the sort of the final sort of learning module that you'll be evaluated on in exam 1. And this topic on functions won't appear in exam 1. So let's take a look at this algorithms. So detecting prime numbers, there's 4 problems here. Listing prime numbers, factoring numbers, generating random colors. Okay, let's look at these problems together because you'll need to do these. All right. And I'm reading the learning objectives here. We've already talked about all of these except for the last one, which is learn about nested branches and nested loops. So you have a loop within a loop. That's what a nested loop is. A nested branch is an if statement within an if statement. All right, let's create the, I'm going to switch over to my new environment here. There we go. I'm going to work in my local console here. So here we have a program that says buy. And it runs. Let's look at this problem here. Detecting prime numbers. Write a console program that asks the user to enter an integer greater than 1. The program determines if the number entered is prime and writes a message to standard output stream stating whether the number is prime or not. And for example, develop 8 test cases. Include the test cases in a multi-line comment. So you can read the details on your phone or computer now. I'm going to start on this one. So we want to prompt the user to enter a number. And we're going to say that number is prime. I see my mistake there. Fix that. So we're going to ask the user, so you have space, you see that? I had 4 spaces. I'm indenting with spaces here, see that? And I'm indenting with a tab here. Like this tab is being rendered as 4 spaces. But I can change my tab to 4 spaces, see? Now it looks like, oh, the indentation is good, but it's not good. because unless I run this command here, my tabs are going to be rendered as 8 spaces. So how tabs are displayed is dependent on your editor and the settings in your editor. So you can't, when you share code with someone else, like the teaching assistant and myself, you can't assume that we're using the same number of spaces per tab in our editors. So if you want to use spaces, don't use tabs. If you use tabs, don't use spaces. Otherwise, it's going to end up looking like this. It'll look broken in our editor, but it'll look okay in your editor. So I'm going to go with tabs, because I like tabs. So enter a number, and I'm just going to, I like that. It reads more easily. It's more consistent with this one. Enter a number, and then we have this condition. Well, let's read the number in. So we'll have a number, say n. We read the number in. And then we have if n is prime, then we're going to print that number is prime. Else we're going to print that number is not prime. So that's what we're going to do. We're going to enter in a number n, and then we're going to decide whether n is prime or not. I'm going to declare a Boolean variable, n is prime. I'll set it to true. And then we'll, in here we're going to, do stuff. And then the result of doing stuff is we'll know whether n is prime or not. If it turns out n is prime, we'll have the Boolean variable n is prime set to true. If it turns out if we find a divisor for n, we're going to change the n is prime variable to false. You see how that works? So let's pretend that n is prime. So we're not going to, this is a stub here, do stuff. Let's figure it out later. I'm just getting some pieces of the program written. Enter a number, 7. That number is prime. Look at that. That already works. Of course, if I put a 6 in there, it's wrong, right? Okay, so this is how you do it. I've got tests. I know some tests pass, some tests fail. When I ask for test cases, let's put the test cases in there in a multi-line comment. So 2 is prime. A 3 is prime. Maybe I'll do one space here. And 4 is not prime. And maybe 9 is not prime. Maybe 11 is prime. I asked for eight test cases. 27 is not prime. Is 29 prime? 1, 2, 3, 4, 5, 6, 7. That's 7. 108. No, I'm going to change that. 42. Not prime. It's amazing that the answer to the greatest question in the universe is not prime. I'm still wondering about that. Does anybody get that joke?
Hitchhikers.
Yeah, good.
Don't panic.
I'm from the very old generation, so you must read history. You like history?
I do.
Okay.
I think if you Google the answer to
Huh?
if you Google was the answer to the universe or something like that, it shows up 42.
Is that right?
Yeah.
Answer to the universe. There it is. See? That's amazing. Well, what's the question? What's the problem? We know what the answer is. And it took 10,000 years to compute the answer, but nobody thought to figure out what the question was. So now they're working on that now, actually. That's the story. Okay, so this joke used to go over really well in the old days, but now it's like 1-2 people get it. That's it. All right, so those are the test cases, and that's a multi-line comment. Now, how do we decide whether n is prime? What do we do? Well, you know, to be prime means that I have no divisor other than one and myself. So one way to decide whether something is prime is, well, let's decide whether it's not prime. So we're going to check every possible divisor, and as soon as we find a divisor, we can say, oh, you're not prime. So we use a loop, and we'll start at 2, and we'll be less than the number n. We'll increment that counter. So we're going to check numbers 2 through n minus 1. See, I is strictly less than n. That means the last I that we consider when we run the body of the loop will be n minus 1. So if the user types in 7, then we'll try the numbers 2, 3, 4, 5, 6. Now we're going to stop. We're going to try to divide 7 by 2, 3, 4, 5, and 6. None will divide evenly. So we will conclude that n is prime. But if the user enters in 9, then we're going to try 2. 2 doesn't divide into 9. And then we're going to try 3. 3 divides into 9. So it must not be prime. See? So what we're doing is that we're searching for a value that divides into n evenly. Once we find it, if I divides evenly into n, once we find it, we're going to set n is prime to false. Well, let's do it like this. You see how the indentation is important there? I got to do that, right? See how I'm doing the indentation? This is the for loop. And I have a single conditional here. And it has, if the condition is true, then I do this one statement. See, we're setting n is prime to true. That's our initial state. And we're going to assume that n is prime. And when we find a divisor, I, if some I divides evenly into n, then we're going to change our assumption by changing the state of this Boolean variable. We're going to set n is prime to false. And we're going to we can continue with the loop, which is wasteful, or we can exit. And to exit the loop, we just issue this break statement.
Is that all you need divides evenly to n on actual computer code?
This here, this is pseudocode. This won't compile. Right?
Oh,
Yeah, Yeah, so that's just for us to read. See, as we're moving toward a solution, we're not just typing in computer code here. We're mixing it. We're starting with human language, and then we're replacing it slowly, gradually, incrementally with the code that the computer will can compile and implement what we want. So here's the problem. How do we what condition? So this if statement, remember, if statement takes an expression. There's some expression here. Some expression that evaluates to true when I divides evenly into n, and evaluates to false when n divided by I gives a remainder. Yeah.
N mod I equals 0.
That's right. That's good. That's exactly what we need. N mod I. So what's n mod I? N, that means n divided by I, but I only want the remainder. So if I divide n by I, and I get a remainder of 0, that means I evenly divides n. So we're looking for a remainder of 0. When we get a remainder of 0, we know that we got a divisor. N is, let's set n as prime to false and exit the loop with a break statement. This is extra finesse here, you know. This just makes it run faster. The other thing is we could also use square root of n here as well. You know, that's sufficient. We don't have to go all the way up to n minus 1. But I'm not going to do that because it confuses people at this point. You're just trying to understand how to write code now. So we're not going to go all out. So we can, the break is sort of optional. If you want to leave that out, this is good enough. Here's good enough for an answer in this class. Okay? The break just makes it run faster. Of course, we wouldn't notice that. We're just talking nanoseconds. The square root of n makes it run faster, but we wouldn't notice that unless n got very large. All right. So let's see. Let's see if it works. Okay, now what I'm going to do, I'm going to be disciplined about this. I'm going to try the test cases. Let's do 2 first. 2 is prime. Let's try 3. 3 is prime. Let's try 4. 4 is not prime. I'm going too fast. 9. 9 should be not prime. 9 is not prime. 11. 11 is prime. 27. 27 is not prime. Not prime. 29 is prime. That is prime. And the greatest number of all, 42, amazingly, the answer to the universe is not prime. We've computed that here. Okay. All right. That's how to do that problem. And, it goes on from there. So I'm going to leave the rest of those for you to work on. We'll talk a little bit more about these to help you with that. But I also want to remind you, this, going through these problems, figuring these out on your own, I recommend against searching on the internet to find code that solves these problems. I mean, that's, you could do it that way, but you're not going to learn anything. Well, you'll learn how to search for code, but you won't learn how to write these things. And then you're missing a learning opportunity, especially if you want to do programming later on as a career. And there's an awful lot of opportunities as programmers. A lot. If you're a good programmer, you're graduating right now this year, and you're a good programmer, you don't have any trouble finding work. You just get a job. And but that's not, if you don't like it, don't do it. So it's not advice to be a programmer. I'm just saying that my advice is if you think you want to do that, don't look up the answers to these. Figure them out on your own. And it's not easy. You got to make an effort. You got to put time into it. And if you don't get the answer right away, sleep on it. Try it the next day or later in the afternoon. So just keep hammering away and develop your skills slowly. It takes a lot of effort. Don't be discouraged. These are simple programs for me, but when I started, I couldn't understand what was going on. I had to think about it and work at it. But don't be discouraged. Don't just look stuff up. Try to work these out on your own. And so that's the advice for doing the labs. And the advice for doing the exam, to prepare for the exam, is start looking at these exams and practice. This is an exam. I gave this in spring of 2014. I'm going to give you an exam that looks very much like this. Not exactly the same problems, but similar. So print these out and try to work these out on your own. And you say, oh, yeah, okay, I did this. I figured it out in my head. Well, now what? He didn't give me the answer. Oh, but you can get the answer because you take this, put it into a sample program, run the program, and then you can figure it out like that. Okay, any questions? That's it then.